Computation only gives you numbers or symbols, but no insight. I don't know what I'm talking about. It explains, it gives you the structure of the Condorcet, a semicolon. It's 6 of them. 1 minus t squared x 1. So this was output by Maple. Sorry, there's one more. Not too big. 1 square x 2 3 1 x 3 1 2. T is really superfluous. We can replace every x by tx. But it's useful, yeah?
How many x's do you want?
1, 2, 3, 4. Oh, you 6 of them. 6 in the bottom.
6 different subscripts?
Yeah, no. Yeah, 1, 2, 3. Maybe I copied wrong. X2, 1, 3, x3, 1, x1, 2, x1, 2. Oh, I copied wrong. Yeah, that's right. Yeah, 1 more to go, sorry. 1 minus t squared x minus 3, 2, x, epsilon, 2, x small. Yeah, one more. Yeah, there's one missing here. 1 minus t squared. So this is the beauty. I'll tell you why I like it so much. Maple outputs this in 20 seconds. And become a computer very slow, and I probably didn't optimize it. Now, if you do Taylor expansion, it's a rational function of t. If you do Taylor expansion, and you look at the coefficient of t to the power n, it's very easy. You expand it, you get the polynomials in x1, 2, x1, 3, and so on. So it gives you the generating function over all Condorcet scenarios. So in this case, it's x1, 2, 3 times whatever. So, and also it explains the inside. It tells you that each of them, so this is 1 to 3, 3 to 1. So 1 and 2 are type, 2 and 1 are type, 1 and 3 are type, 3 and 1 are type, and 2 and 3 are type. So this corresponds to Condorcet type. But the numerator makes it discrete things. So basically you have these basic vectors, the original paradox and its square, and then it just tells you the structure. It tells the structure of this discrete cone. So it has lots of insight. In particular, if you only care about the enumeration, you plug all the x's to be 1, and you have a generating function for the actual enumeration, and you have a beautiful generating function in T alone. And we're going to reprove completely rigorously what I proved in class, in my class this afternoon. So it's 1 plus t squared from 1 plus t cubed times t cubed. Yeah. So if you set all the x's to be 1, now it's straight enumeration, not weighted enumeration. Ta-da! That's what you get. That's a simple generating function. So the coefficient of t to the power n here is, if you do Taylor expansion with Maple, is the exact number of Condorcet scenarios with n. Of the first kind. To double it, to get both kinds, you have to double it. But what if I want the even one? If I want the even one, I don't need this. So the coefficient of t to the power 2n minus 1 in the rational function t cubed times 1 minus t squared to the power minus 6. The same thing, the coefficient of t to the power n in this. Or better still, the coefficient of this. Or better still, the coefficient of this. Let t squared be s. So it's minus 6, choose n minus 2. And this is a beautiful polynomial, and that's a rigorous proof of what we got empirically before by getting the polynomial. If you divide it by the other one, was minus 6, choose 2 and minus 2. So this is the complete proof of the Gerlein-Fishbone theorem. So this is this part. But what about the real things? 1 over 16 is not the true things. In real life, most vectors are very unlikely. What if you, every voter votes with probability 1/6, take one of this. So then what you need to do is look at the grand generating function in x1, x1, 2, 3, or the 6 variables corresponding to the 6 permutations, and do a substitution. Once you expand it, you do what Giancarlo Rota calls an umbra substitution. Instead of setting all the x 1, 2, 3, etc. to 1, you do the following substitution, and I'm very excited about this. So this is a brand new general theorem. It was motivated by something a little bit frivolous about some paradox by some obscure French social scientist way back a long time ago. But it led to a deep, in my humble opinion, theorem that I'm going to tell you soon. But let's do it in this context. So we have a general power, x1, 2, 3, alpha 1, x1, 3, 2, alpha 2, and so on, alpha 3, x 3 to 1, alpha 6. So before, what we did is goes to 1. But what we should really do, replace every such monomial by the multinomial distribution. By alpha 1 plus alpha 6, which is n by convention, over alpha 1, 6 to the power n. This is what we should do. Now we get the real probability of these scenarios. Because the probability of getting alpha 1 of this with a fair die. So it's a fair die. And you can even make it more general with probabilities. It still works. So after we do the transformation, you can do it. Use the following fact. That this operation is really the constant term of the 1 de la plus the n, the 6 to the power alpha 1 n over z1 to the alpha 1. Constant term. So you apply it, get a constant term functional, but constant term is really a contour integral. So at the end of the day, you get this rational general function in t and x1, 2, 3, etc. and get a 6-fold contour integral of this huge monster over this variable, dz1. And by the fundamental theorem of Zeilberger theory, this is guaranteed to be a solution of a linear recurrence equation with polynomial coefficients. So it's an upgrade. Before it was a polynomial or rational function, more generally. Now it is. But since we know a priori that it is a solution of a linear recurrent equation in polynomial coefficients by the general theory, and there is a maple package for doing it that does successfully double integral, triple integral, but to be honest, 6-fold integral is beyond the scope of my computer. Maybe I have some colleagues in Austria with their computer, you can do it. But who cares? Since I know this recurrence exists, using this algorithm, this Ullmann substitution, the computer can crank out enough values. 60 terms was easy enough. And that's what it did. And it got empirically, but it's identified rigorously, a linear recurrence equation with polynomial coefficients for this probability. Or rather, with this probability times 6 to the power n. The numerator. Then you have to divide the 6 to the power n, or 6 to the power 2 number 1. So here is another great announcement today. theorem. Let AN be the probability under the multinomial distribution. So now it's a fair die like we did, not under the stupid thing with the thing. Probability of 2n minus 1 voters with uniform, where everybody votes equally likely to each of the three rankings and getting a Condorcet paradox. And for the sake of Niels Sloan, and to be an integer sequence, times, so it's a numerator, times 6 to the power 2n minus 1. To get the actual probability, you have to divide by the total number, 6 to the power 2n minus 1. There's the probability of the n. Is the following: an plus 3 equals 4 times da 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 da. I'm too lazy to write it. Some specific third order recurrence equation. So once you have the values for A1, A0, A1, A2, you can crank out thousands, 10,000s of values. And you can do asymptotics and divide by this, you get the following semi-rigorous asymptotic formula. And this is a Condorcet, Zeilberger constant, which I'm very proud of. So the probability of the genuine Condorcet paradox happening as n goes to infinity tends to, and now it's really big because the historic moment, 0.08. So it's more. Before it was 0.625, 6.25%. So it's 8.7739 82 80 45 910 da da da. Computational challenge to all you computer hackers out there if you listen to it. Compute the Condorcet Zeilberger constant to 1,000 digits, to 10,000 digits. Like they have the pi contest, why not have a contest for this? So see how far it can go. So this is. So it's more than 6.25%. If this is new, more visible methodology is 8.779. So this concludes the first part of this talk, the Condorcet paradox. The other one to do with voting is also due to two now 19th century Frenchmen, Bertrand and André. And that's the famous ballot problem. And my favorite combinatorialist, Major Percy McMahon, generalized it to many candidates. And being a very educated person, he quoted in the original French the article of Bertrand. Anybody here speaks French fluently? No, you speak? Okay, want to read it? Okay, but you have a good accent? Okay, Pierre et Paul sont soumis à un scrutin de volontaire. Okay, I want the Bible then. Pierre and Paul are subject to a ballot election. The urn consists of M bulletins in favor of Pierre and N bulletins in favor of Paul. M is larger than N. Pierre will be elected. Pierre will go be elected because M is bigger than N. What is the probability that during the counting Pierre was always strictly ahead of Paul? So you can write the thing in terms of a two-dimensional walk. So you start at 0, 0, and you have M votes for Pierre and N votes for Paul. And M is bigger than N.
It's really Peter and Paul.
Sorry, oh, so no. Was Peter and Paul? Pierre and Paul, no, Pierre and Paul. What?
In English, it would be Peter.
Oh, okay, but it's... I know how to pronounce Pierre. Thank you, Pierre. Okay, Peter, you want Peter? Okay, I respect him. Me likes Peter better. So every time there is a vote for Peter, you go 1 unit here. Every time there is a vote for Pierre Paul, you go here. So one possibility is Paul gets so excited. He's leading ahead. He's going on TV and announcing, I'm the winner. But then Twitter catches up and football embarrassed himself. So at the end, so this could happen.
See, Paul, this is what happens when your platform includes discrimination against procrastinators.
And something like this happened in Israel about 20 years ago. One of the electors announced himself as a winner, but because it was partial vote at the end, because it was a close vote, the other one wound up winning, so he embarrassed himself. Anyway, the total number of walks from 0, 0 to mn is obviously m plus n should m. So there are two versions, the weak version and the strong version. So sometimes you're allowed to have ties, but in the original version, except for the very beginning, Peter was always ahead. So what is the probability that Peter was always ahead? So the first step must be this, and in general, the m plus n should m. So how many of them, how many walks never cross the diagonal? And André has the proof from the book for this. It's called the reflection principle. That is very, very beautiful. Suppose it's a bad walk. Suppose it's sooner or later, so you have to start with 1, 0. So suppose it's bad. It could be bad several times. Look for the first time it's bad. First time it crosses diagonal. And reflect it. And get a walk to the point -1. No, the point 0,1. Sorry. The point 0,1. That's the version. Every walk from 0,1 to m, n must cross this. So every walk from 0,1 to m, n is a bad walk. So the number of bad walks from 0,1 to m, n is essentially the number of bad walks from 1 to 0. But since all the walks from 0,1 to m, n are bad, the number is m plus n minus 1 choose m. And so the number of good walks is this. So the probability is this, and it's simplified exercise from running out of time, is m minus n over m plus n. In particular, if m equals m plus 1, it is 1 over 2m plus 1. Beautiful closed form formula. So this, thank you for your attention.
Should it be m minus n plus 1? And then over m plus
No, it's m minus n over m plus n for the strict. For the
strict, okay.
Yeah. This is the other version, this is weak. Okay, thank you very much.
In the first part of your talk,
That equals 0 checked out.
That's
in part 1 of your talk,